Okay, this is the last video for uniform circular motion, and it is about torque. And no, kids, don't get excited. I did not say twerk, I said torque, which is something very different than twerking. So the objectives of this video is that by the end of this video, you can say the following statements. I can define torque and describe its applications, and I can calculate torque. So let's ask the question, what is torque? The definition is that torque is the ability of a force to rotate or accelerate an object around an axis or a pivot point. So if a force is able to spin something, then that means there's a torque on that object. Our equation for torque is that torque equals Rf sine theta. This weird symbol is actually the Greek letter tau, and we use that for torque, and the units of that is in Newton meters. R is radius, again in meters. F is force in newtons, and sine of theta is going to be the angle between radius and force. So RF and sine theta are all obvious. The only new symbol that you are learning is tau for torque. So here's some examples. Let's say you have a merry-go-round, and you're pushing on the outside. Okay? The reason the merry-go-round spins around this pivot point is because you are pushing on a force, and that force is acting over a radius of the merry-go-round. Okay? And so as you can see, this little statement down here says F needs to be perpendicular to R for a maximum alpha. And alpha is angular acceleration. So if you want this thing to spin as fast as possible, you need F to be perpendicular to R. And so let's look at this example, and we'll talk about the perpendicularity a little bit more. So in this example, if you wanted to spin, let's say the girl sits down on the seesaw, and this is after, okay? The radius between her and the pivot point is this. And again, we draw it from the pivot point to her, okay? The force would be the force of her weight, which is gravity. So the force is pulling straight down, right? But only a part of this force is actually helping the seesaw spin in that direction. Because when we break down the vectors into the component vectors, you see that this part of her vector, which is horizontal and parallel to R, that doesn't do anything to spin this object. It's just really pulling against this, which is not going to help it spin. The only part that helps it spin is this part that is perpendicular, makes a 90-degree angle right here to R. So that's why there's a sine theta thrown in our equation, is because we only really want this force part of the force. Okay? So here's a person tightening a lug nut on a car. Okay? The radius again is going to be the distance between the pivot point and the force acting on it. If the person is pushing down with that force, again, when we split the force into the two component vectors, the only part we really care about is this guy, because this is the only part that is pulling the wrench into a circular path. This part is just pushing against the radius and won't help it move at all. Okay? So now let's look at a conceptual question. Here's two wrenches with the person pulling one halfway at the wrench and one at the full way. The question is, which one is easier to turn? And so intuitively, you should probably say the second one, because you've done this before in real life and you realize it's not really easy to pull and twist a wrench when your hand is way up close like this, okay? But why mathematically does that work, okay? Well, so let's say that you are going to tighten this lug nut or this nut, whatever, to a torque of 1 Newton meter. That's usually the standard in the car industry and any other industry for tightening objects like screws and nuts and bolts is to a certain amount of torque. So let's say you want to tighten it to 1 Newton meter, and your distance away from your hand is only 0.1 meters from this radius right here, which would mean that you need a force of 10 newtons to do that. Okay? So then what if you move your hand twice as far? Well, so now if the distance is 0.2 meters, then I only need a force of 5 newtons to get that 1 Newton meter torque that I need to tighten this thing up. So you can tell that by doubling the distance from 0.1 to 0.2, I halved the force required. So which one is easier to turn? Definitely the second one, because it takes about half as much force with half that length. Okay? So here's an example that you might come across. A wrench is used to tighten a lug nut on a tire. The required torque is 50 Newton meters. What force must be applied if the length of the wrench is 20 centimeters? Okay, well, so when I think about this and I look at my givens, I automatically know that radius is going to be 0.2 meters. You'll be like, how did you get that? Well, this is 20 centimeters, so remember that there are 100 centimeters, or centi is times 10 to the -2, so I move the decimal place twice, and I get 0.2 meters, okay? The torque that I require is 50 Newton meters, and I want to know the force, okay? Since they didn't give us an angle, that means I don't need an angle. I have to assume that the force being applied to the wrench is going to be perfectly perpendicular, and that I don't need an angle. So this is my torque equation, right? If they didn't give me an angle and I don't really need it, then it's just going to be R times F. Okay, I plug in my numbers and I find that F equals 250 newtons. So it's pretty simple, easy peasy. Okay, so what we are going to spend most of our time in class talking about is equilibrium. And most of you are familiar with the first condition of equilibrium being that all the forces have to add up to 0. So when you talk about you sitting in your chair right now, we say that you're in equilibrium because all the forces acting on you right now add up to 0. The chair pulls you down, gravity pulls you down, the chair pushes you up, and those two balance, and the sum of your forces are equal to 0. But equilibrium actually has two conditions. One, that the forces have to equal to 0, and the second condition is that the sum of the torques also have to equal to 0. If both of these conditions are not met, then you are not at equilibrium. You have to have both forces and torques all add up to 0. And here's an example of what I mean. So let's say I have a bar of some sort, like maybe a meter stick, and I pull up and push down, and both of the forces are 10 newtons. According to the first condition, you would tell me that the object is at equilibrium. It's not going to move at all because all the forces equal 0, 10 up and 10 down. However, if you think about this in real life, you intuitively would know that this bar is not going to stand still and actually is going to be rotating clockwise because, guess what? The second condition is not met. The sum of the torques are not equal to 0 when you do this because you have a radius and you have forces. So these torques are not going to balance out. So in the end, this is not an equilibrium because even though the first condition is met, the second condition is not. So we are going to spend a majority of our time on Wednesday and Thursday talking about this and doing some cool and fun examples of balancing stuff. So look forward to that. So is this the end? Not really, but it's certainly the end of this video. Good night and good luck.